Right. Well, welcome everybody. Not sure who the track host is, but I'll introduce myself. So my name is Nicki Watt, and I'm going to be talking to you today about the sort of tools and approaches that are used to automate the creation of self-contained, secure environments in different clouds. So just a little bit about me really quickly. I'm a hands-on lead consultant at a company called OpenCredo, co-author of the book Neo4j in Action, which is about graph databases. But I'm currently working with a department in the UK government on their sort of cloud automation project. And a lot of what I'm going to be talking to you about today is kind of based on that. I was asked by Francisca to kind of talk on infrastructure-related stuff. And I think this talk is probably going to be quite different to some of the talks you've kind of been to already. It's not doing a sort of deep dive into one kind of particular technology, but rather we're going to look at the sort of overall sort of approach and tools that we use to solve this problem. And that's my Twitter handle if you want to tweet about this or get hold of me later. So the agenda for the talk is that we're going to have a look at what is the actual problem that we're trying to solve, what are the options out there to do this kind of stuff, and then we're going to look at how we've gone about doing that and finish off with a conclusion. So first up, what is the actual problem that we're trying to address here? So the cloud market has evolved quite a bit over time. You started off with Amazon as the major kind of player, but now you have the likes of Google and Azure and smaller players in the sort of OpenStack space as well. And many organizations have successfully managed to embrace cloud computing. You look at the likes of Netflix, and their use of Amazon is a good example. And a lot of this was initially to sort of drive down costs, get out of your data center, take advantage of commodity computing. But nowadays, one of the sort of big driving factors is also to really be able to sort of innovate and gain a competitive edge. So, people can react faster and experiment in the cloud much quicker than they can, obviously, if they have to have their own machines. Also, with the elastic nature of cloud, it's easier if your business has got a sort of spiky kind of load, it's easier for you to scale up resources and scale them down as and when you kind of need them. So many have done this successfully, but for many sort of traditional sort of enterprises and more traditional organizations, they found this very difficult. And as I said, there's lots of different clouds out there now. And what people find is that you have developers doing one thing in Amazon and a set of tools there, and they're doing something else in OpenStack and something else in Google. And for the sort of traditional sort of IT operations, it's very unclear to them how is this stuff actually being created in the cloud? Is it secure? Does it address all of the kind of things that they're interested in? There was a great sort of unease here to the extent where they thought, well, maybe we'll kind of steer clear of this cloud computing thing. But instead of throwing the baby out with the bathwater, many organizations, and the government is one of these, has realized that actually, if we can do this process in a more sort of efficient manner, at least as far as they're concerned, you can still reap the benefits, but still have the level of confidence that the way these sort of machines and things are created addresses all the concerns that they're interested in. So when a dev team comes along, rather than simply arbitrarily spinning machines up, they want to make sure they have a repeatable, verifiable, and maybe an auditable way in order to create these environments. And I'm talking about cloud computing in a broad sense here, so it's both public and private cloud. So first and foremost, we want to create secure, repeatable, verifiable environments. But besides this basic premise, we also want to be able to move cloud providers. And the reasons for this can vary. They can be strategic or financial. They could be sort of technical. Maybe one cloud offers better latency or IOPS guarantees than another one. Or you may have workload requirements. So you may say that I'm very happy to run certain development workloads in the public cloud because there's no content that's sensitive. But if I'm going to run in production, I want to run somewhere else because I need more guarantees around that code. And whatever the reason, avoiding vendor locking is becoming a very popular request nowadays. So the summary of what we're trying to solve is that we want to see how can we create fast, repeatable, secure environments that can run in different clouds. And we're really going to try and solve this from two angles as well. We want to make sure that it's, from the dev's perspective, it's done fast and obviously not kind of held back by bureaucracy, but from the management perspective in a way that they're going to be happy about this. So this is not a small undertaking. There's a lot to sort of consider here. And although we're kind of keeping an eye on public and private, what I'm going to be talking to you about today is how we've done this specifically in the public cloud sector. So whether you're a team in India or whether you're a team in the UK, If you want to request a new environment, you should be able to get that environment and have it spun up in an appropriate cloud provider for you to use. So for the rest of this talk, I'm going to use a sort of concrete example to describe and illustrate the points that I'm talking about. So let's say that you're team one. Maybe you were in the talk I think it was about 2 talks before this, where Martin was talking about concurrent programming in Java and taking advantage of new sort of latency stuff. Maybe you want to build the next big sort of trading platform. That in itself would be one environment that you might want to spin up in the cloud. But for the purpose of this talk, let's say that you also need a tooling environment, somewhere where you can build the sort of microservices or whatever it is that's going to be involved in your next big sort of trading platform. So you might identify, I have some key functional requirements that I need to be created in my environment. So you might say, I'm going to do continuous integration and delivery, and maybe I want to use Jenkins for that. Maybe you decide, well, actually, I need a few slaves in there as well because I'm going to be building lots of things. And maybe you also want sort of Jira or something for project management. And you can't make use of things like Travis or whatever because you need to be in a secure environment. Once the sort of fundamentals have been established as to what your environment looks like, you as a team just want to come along and say, I'm team one, I want one of these environments, I want 3 slaves, this is the DNS entry I expect to go to on the internet to get to my environment. And by the way, these are the SSH keys I want to be able to log into the box with. So besides the functional components that the environment has, there are also some sort of supporting services which are very handy irrespective of what kind of environment is being spun up in the cloud. So this, for example, is things like DNS. So you can use IPs everywhere, but if you have a portable DNS service that can be used within your environment, that's handy irrespective of whether it's a tooling environment or some kind of trading platform. And we want to make sure this is completely sort of secure, so it's going to be private, but we will need some kind of VPN access or a VPN service to be able to get into that. So what are the options if we want to do this? What are the options out there already? So we want to define this template, and we want to be able to spin it up in kind of different cloud providers. As soon as somebody says the word sort of multiple or hybrid clouds, you will inevitably kind of run into what people call the cloud management platforms. And these are various commercial as well as open source tools which claim to be a sort of single pane of glass. And they say that we can do everything that you need to do in multiple clouds. Be that provisioning, be it config management, be it monitoring, they can do it all. And some are better than others, and there is a place for them, but they all tend to suffer from the same problems, and that is, in trying to be all things to all people, they tend up mastering none of them very well. They also impose their approach and tooling and workflow on you, and with the cloud market moving so fast, if there's sort of features in the cloud that you want to take advantage of, if it's not in your CMP, then it's tough luck for you, you can't make use of it. So instead of sort of opting for this one-size-fits-all container management platform solution, we've gone more in the sort of CodeMesh style, which promotes looking at the right tool for the job. So is there a way we can find the right combination of tools to still achieve what we're trying to do and come up with a solution? So this all sounds fair enough, but you can't arbitrarily try and throw a whole bunch of different tools together and hope you're going to get a cohesive solution out of that at the end. You do need to think about how you're actually going to structure this and put this stuff together. So I think the key to this for us is to ensure that we have a set of principles which drive the tools that we choose and also the way that we choose to integrate them. And then provided we stick to our principles, we can potentially swap out tools as new options and technologies kind of come along, but we don't sacrifice the overall goal that we're trying to achieve. So this doesn't mean it's going to be completely seamless when you try and swap these things out, but rather that you've at least planned for it and it's more easy to adapt. So the principles that we follow can be described by an ASAP acronym. So in order to do this stuff, we believe you need to automate everything. So the goal here is to have a transparent process for creating fast, repeatable environments. So we don't want any humans in the loop. Humans they just slow things down. Manual configuration is error prone, and that just causes lots of problems. So we need to automate everything. One of our goals is also flexible environments. This is both from the fact that we want to move cloud providers, But also, if we have different tooling that we want to swap out, we want to be able to do that if we want as well. And in order to do this, we believe you need to separate your configuration from your code. And you need to do this so that it will allow you to swap and change things a little bit more easily. The other thing is that it might sound a little bit obvious, but you need to have a cloud provider that provides an API for you to integrate with, as well as the tools that you use. There's a lot of cloud providers out there they call themselves cloud, but they aren't really, and you've got to go to portals and push buttons and all kinds of things, and that really just doesn't work in this type of scenario. So both the tools and the cloud provider must have an API to integrate with. And although we certainly don't discount any commercial tools out there, our preference is for modular open source tooling if it's available. So what I've described is sort of, there's two broad areas. There's sort of the self-service functionality. So if a team comes along and they say, this is my environment and I want to be able to choose this cloud and put this information in, that's the self-service part, which we're not going to look at. We're going to assume all of that's done. We have the inputs as to what they want. Now we're going to look sort of under the hood at what the tools and approaches are in order to spin this stuff up. So on to the sort of actual meat of the talk, where we're going to have a look at the challenges that we encountered, some of the sort of lessons learned, and the tools that we used in our journey along the way. And we're going to cover 4 areas. We're going to look at infrastructure provisioning, config management, and then securing all of this stuff, and then moving it. So the first challenge is automated infrastructure provisioning. So this is about creating the various different resources in the cloud. And what I mean by that is things like networks, your firewall rules, your security groups. So all of this stuff can be automated by a cloud provider. And given our sort of example CI scenario, maybe we decide, I want 2 networks. I want one to have the sort of supporting services, and I want another one to have all of my stuff in it. We also want to bring our own VPN software in this case. We want to make it sort of portable across clouds. So instead of using a cloud provider, we will bring our own VPN software, and that will be in the supporting service. And depending on whether you land up doing this in sort of Amazon or an OpenStack provider, what you'll find is that conceptually they have very similar components, but their APIs are fundamentally different. You cannot code to an Amazon API in the same way that you code to an OpenStack or an Azure API. And the lesson here is that there is no such thing as a single common cloud API. There are libraries out there that try to abstract this for you and give you a common sort of API into the different clouds. This is things like libcloud and jcloud. But all that tends to do is it lands up confining you to whatever the lowest common denominator is that can be found across all of the clouds. We didn't really want to confine ourselves to this. If there are some features in a cloud that you want to take advantage of, we want to be able to do that if we so choose. So we want to really sort of deal and embrace the fact that there may be different APIs out there, but we still want to be able to move stuff around. So we want a tool that can look to handle this. And the tool that we've chosen in this space is a tool called Terraform. Just a show of hands, has anybody heard of Terraform, used it? Oh, okay, that's good, cool. So this is an open source product from the guys at HashiCorp. You probably know them from the makers of Vagrant. And Terraform is really there to sort of create, manage, and manipulate your infrastructure resources. And the way you do this is that you define your resources in one or more files. And these resources define the target infrastructure that you want to create in the cloud. You then have a sort of command line tool which operates on these files, and it takes what you've defined and it ends up creating those things in the cloud itself. So Terraform, out of the box, supports all of the major cloud providers. You've got things like sort of Google and Amazon. You also have other sort of smaller players like DigitalOcean, OpenStack, etc. And unlike the libraries that try to make a common API across all of the cloud providers, Terraform's architecture for the way it interacts with different clouds is to have a plugin architecture. And it expects the plugin to be able to fully understand the API that it's talking to. So if you have a Google plugin, it needs to understand the Google API. And if you have an Amazon plugin, it needs to understand all the features that Amazon is capable of doing. And the commonality is then, this is then brought about and made available in the DSL for you to code against. If you were only going to do this in one cloud, so say now you were only operating in Amazon, the equivalent tool would be something like CloudFormation. That's what you would use for that. If you were only operating in an OpenStack world, the equivalent would be something like Heat. The nice thing with Terraform is that it allows you to combine things from different cloud providers in the same definition. So let's have a little bit of a closer look at what this DSL looks like. So the DSL is custom to HashiCorp, and it tries to kind of strike a balance between being human readable and editable, as well as machine friendly. But if you don't like that, there is also a JSON format. So each resource within Terraform represents an individually controllable entity in the cloud. And this is generally identified by this resource keyword. You can see that we've got a sort of compute resource at the top there, and then we've also got a pool of public IPs where we want to extract a floating IP out of. The naming is kind of important here. So the first part represents the provider you're going to. In this case, we're targeting OpenStack. And the second part of the name is the type of resource that you're creating in the cloud. So in the top, we've got our compute resource, and the bottom one is a floating point IP. And then you can also give this resource a sort of name or an alias. And we'll see that this becomes important later, because what Terraform allows you to do is for your resources to refer to one another and reuse information about itself. So this is essentially the sort of AWS equivalent to what you just saw on the previous slide. So it has slightly different variables, and it's got maybe slightly different concepts. And that's because, as I said before, the APIs are fundamentally different. But the nice thing with Terraform is you could put both of these together in the same definition if you wanted to. So Terraform also covers more than just your traditional compute resources. It can also have provider plugins for things like PaaSes, so Heroku and Cloud Foundry. There are plugins for that. There's also plugins for software as a service, so things like DNS Simple or Mailgun, anything with an API in the infrastructure that you can control, you can potentially have a plugin for that. And this proves extremely useful when you want to combine infrastructure from different providers. And this is exactly the case that we have in our example scenario here. So we've said that our teams have specified a DNS entry that they want to say, when I go here, this is where I expect to go in order to be able to VPN and get into my cloud. And Terraform allows us to create an entry, one for the external DNS, and separate infrastructure to create it in whichever cloud has been spun up. So whether it's in sort of Amazon or in an OpenStack, it doesn't matter. We can combine the two together in one place. And although we're not kind of handling it here, in theory, you could have an active scenario as well. So you may want to load balance across clouds. So you may create some infrastructure in Amazon, some different infrastructure in OpenStack, and you can create an entry in your DNS provider which will allow you to load balance between the two clouds. So here we just have an example of the external DNS entry. In this case, we've used Amazon's Route 53 service, but you could use DNS Simple or whichever sort of provider you're looking for. So Terraform also provides the ability to handle variables. So we have some information that we want passed into this process that we can configure exactly what it is we're creating. And Terraform allows you to do this by having whatever variables you decide you can refer to those in your resources. And within the DSL, the resources can refer to one another. And Terraform is clever enough to understand dependencies. And when it understands those dependencies, it will ensure it creates the physical resources in the right order as well. So the example here is that in the middle, we've said for OpenStack, out of my public pool of IPs, I want to extract a floating point IP, and I want to use that in other places. So that gets assigned to an address, a variable called address. And you can see that that is now being referenced in the top section, which is the compute resource, which says, take that value and assign that to me as my IP address. And in the same definition at the bottom, we've got our Route 53 record, which says, take that same IP and configure it in my A-list record so that you can route me to my particular VPN box in the cloud. Other kind of stuff that it can do sort of user-controlled resource scaling. So you can do Amazon scaling, Amazon sort of auto-scaling, but you have an ability to do something kind of similar with Terraform, where you can kind of say, in our example, maybe you want 3 or 4 of these Jenkins slaves boxes in your environment. So you could pass an account and you could say, I want 4 of them, and Terraform would ensure that it created 4 of those resources for you. If you change it, you'd have 2 or whatever it is that you were looking for. Terraform is not just for creating stuff, though. You can also use it to maintain your infrastructure whilst it's there. So I kind of call this the diff for infrastructure. And when you do a Terraform apply, so that takes your sort of resources and your definitions and applies it to the cloud, it keeps track of what's happened in the cloud provider. And it stores this state either locally or in a remote database. And whenever you make changes to that definition, it will have a look at what you've changed. It will have a look at the cloud provider, and it will say, this is what I'm going to do if you execute me. So the example up here, it's a little bit, you can't really see that, can you? It's not great. But the top level is essentially saying, I'm going to create an OpenVPN box in this setup. It hasn't existed before. But in the bottom one, it's saying, oh, I see that you've actually changed from a medium-sized resource to a large resource. And in this case, I'm going to have to completely destroy that machine and recreate it for you. But the nice thing is that you can run this plan and you'll completely understand what it's going to do in the target cloud provider for you before you do it. And then you can either choose to act on it or not. So the sort of summary for the sort of infrastructure as a service provisioning side is that we found a tool that kind of adheres to our ASAP principles. We've automated everything. We've managed to separate our sort of configuration from our code so that we can code things differently in different providers. It's API driven, and our preference for a sort of modular open source tooling product has been adhered to. As I said, its key kind of selling point is that you can combine infrastructure from different providers in the same definition. Terraform is very new, though. It is still evolving, so it's only on version 0.66 at the moment, and it does have a few pain points in its kind of DSL. We've managed to work around those, but we did have to jump through some hoops to kind of make it happen. It has a meta-programming model as well, which is quite interesting, but we won't go into that at this point. But there are other alternatives out there as well. So the whole point of this is that there may be other things which can do this better, and maybe you want to try them out. Examples are things like Tosca and Cloudify. Again, a very, very new, still quite an immature product. And when we looked at it, we preferred Terraform at this particular sort of stage. So we went with that, and it's worked out really well for us. So before moving on, it's worth mentioning, how do we get consistent images in different clouds? So you may have noticed in the Terraform file that when you create a compute resource, one of the things you tell it is that this is my base starting image within the cloud. But if you're going to start in Amazon, a CentOS image there is potentially slightly different to a CentOS image in some other kind of cloud. And for the purposes of what we're trying to do, we want to ensure that the starting point is the same. It's got the same operating system, the same packages, same everything. And in order to do that, we use another HashiCorp tool called Packer. And Packer's responsibility is essentially to provide you with a way where you can have a kickstart file or whatever the particular mechanism is for auto-creating your images, and then it can upload it and into the different clouds. So by doing this, we've managed to have a sort of a single definition of what we want our starting image to look like, and we upload that into all of the clouds that we intend to go to. And we know then that moving forward, everything beyond that can be consistently applied. So moving on to the second challenge, which is automated config management. So we've automated our infrastructure. This is great. We've tied it together at a macro level. We've got our consistent sort of OS images. But now we want to zoom into the actual kind of boxes themselves. And how do we get the software on there? How do we tie up some of those services that we might be starting up at a more sort of micro level? And there's two aspects to this challenge. There's how do I do it the first time round, and then how do I do it for sort of longer term maintenance? We're going to focus on the sort of initial bootstrapping phase. So the lesson here is that we've made a conscious decision to decouple Some of you may get the reference to that or not. We've made a conscious decision to sort of decouple the initial bootstrapping process from the actual config management tool that's used to do the heavy lifting. So what I mean by that is at boot time, this sort of bootstrap process, what we expect it to do is the very first things that have to happen when a machine starts up. But then we expect it to kind of act as a bridge and to be able to install a particular config management tool of choice and then delegate to it to do the rest of the heavy lifting, whatever that may involve. So there are already a lot of really good config management tools out there. You have the likes of Puppet, Chef, Ansible, Salt, and we're not really going to focus on those per se. There's a lot of detail out there about that. Rather, I'm going to focus on something called cloud-init and the role that it plays in this bootstrapping process for us. So this is where we left off. We have our infrastructure. It's been created in our different sort of various providers, and the VMs have just been started up. Thanks to Packer, we have cloud-init installed on all of the images, so we know we have a common starting point. On boot, when the image comes up, cloud-init is triggered, and it obtains and it runs some automated scripts on that VM. The way that, and ignore this bit over here for the moment, we'll come back to that. The way it does this is, just first of all, so cloud-init is basically designed to work across cloud providers. It is an open source package, originally from the guys at Canonical, and the code is on Launchpad if you're looking for it. And the way that it works is that it tends to work in conjunction with something called a metadata service. So all cloud providers tend to provide this for you. So when your instance boots up in a cloud, there is this metadata service that you can programmatically query and say, tell me about my machine that's just started up. So that will tell you things like what your IP address is, the private IP that may have been allocated to you. But you can also inject some custom sort of user data information into that service and say, when my machine starts up, give it this piece of script or whatever, and it should run that in order to do whatever you want it to do. And that's exactly what cloud-init is doing for us. It's hooking into this metadata service, and it is getting hold of some configuration script that we've passed in and said, I want you to use this as the initial bootstrapping mechanism. So what does this config look like? With cloud-init, you can pass in either a sort of a normal script, it's bash script or something, or there's something called cloud config in a sort of YAML format. And this is an example of what a cloud-init config would look like in YAML. So you can see you can do things like set the host name. You can get it to manage your initial etc host files that you can maybe get out to the internet and be able to download stuff. You can bootstrap a config management tool so that you can use that in order to kind of move forward. And you can also run arbitrary kind of commands and install software if you want to. So that's great. How do we get this thing into our actual instance? So we know that we're using Terraform as the way to do our sort of interaction with the IaaS layer. So one of the things Terraform provides is a template resource, and you can point it at a file on your disk which will say, this is the cloud config that I want injected once all the variables and things have been melted together at runtime. I want you to make that available and pass it into my instance when it starts up. So when it gets created, that will be put into the metadata service, and when your instance boots up, it will take that and start executing it. So Terraform is finished, user data is injected, cloud-init has been kicked in. In our setup, we have one box, which is the big box, which is kind of like a designated orchestration box. And we use this to install and have some of our supporting services, things like our DNS service and some of the stuff that we use to bootstrap the rest of the environment. So its cloud-init process goes something like this. It does its basic kind of initialization, setting host names and things like that. And as part of the user data, we pass in a one-time security token. This token is used to access a secrets management service called Vault, which I'll talk about a little bit later. And so essentially what it does, it will use this token, it will connect to our secrets management service, and it will download some of the secrets that it needs in order to continue its process. From our perspective, the next thing it does is it goes and it connects to our Git repository, using the credentials that it just downloaded from the secrets management, so the credentials to get, and it downloads our config management code that we want it to run. It then initiates a Bootstrap sort of Puppet run on itself, so we're using Puppet in this particular case. And it lands up installing two pieces of software, as far as we're concerned, that are important. One called FreeIPA. This is something from Red Hat. And this provides us with our internal DNS. And this is the portable sort of internal DNS service that we use in the different clouds. It also installs a Puppet master, and that's the thing that we use to help us bootstrap all the rest of the machines and do the config management. So all the other boxes have a slightly different process. So once this box is up, we have a DNS service, we have a Puppet master, it has a DNS name. The other boxes are configured to wait until it recognizes that the DNS service is actually ready. It will then connect to the DNS service and say, register with it and say, give me a domain so that I can then start doing the rest of my stuff. It's also configured to wait until the Puppet master is ready, and then it will ask the Puppet master to initiate a run on the boxes themselves. And that will then go about installing whatever software it is that you want to convert your boxes into whatever it is that you've decided. So in our case, we've got a few kind of Jenkins slaves down there, but we also have our OpenVPN box up there in our supporting services. So we use OpenVPN as our sort of portable way of being able to get into different cloud providers, irrespective of the cloud provider that you go to. And we have our Puppet code essentially configure that box. So why Puppet? There's a lot of, there's more modern tools out there. People say, what about Ansible and SaltStack and, all these kind of things. We actually started with Ansible, and it was a great way for us to get up and running. It's really a really good config management tool. But in this case, the client had skills already in the sort of Puppet side of things. And so we essentially needed to change from Ansible to using Puppet. But because of the way that we kind of set things up, it wasn't a complete sort of easy thing to swap it out, but the mechanisms that were put in place by the principles that we had meant that it was easier to do that. So the summary on this kind of section is that, again, we've stuck to our ASAP principles. Everything's automatable, both from cloud-init's perspective and the config management tool itself. Separated our configuration and our code. Everything's API drivable, and we have managed to prefer sort of open source software. We also have an asynchronous bootstrap process. So what I mean by that is there's no explicit call required from the outside in order to make the config management stuff happen. Once Terraform starts up, the config management just happens as and when it's ready. Because of cloud-init, as they boot up, the services start installing things and waiting for things to happen. So you just initiate the sort of environment, and it all kind of goes and takes care of itself as and when things are ready. By comparison, what I could have done is we could have used, there's some functionality in Terraform where you can have a provisioner, and you can say, when I'm finished, all of my infrastructure stuff, go and call Puppet or go and call sort of Chef or something like that. But we didn't want to have any kind of coordination logic on the calling side. We just wanted that to sort itself out in the environment. And as I said, this approach has helped us to kind of swap Ansible and Puppet out. So one of the sort of last bigger challenges that we're going to look at is how do you go about securing all of this stuff? So security itself is a massive topic, and we're not going to have time to obviously cover it all. We've covered some aspects and mentioned some aspects of this, like, for example, perimeter security. All of our configuration for the firewall rules, the security groups, all that kind of stuff is infrastructure as code in our Terraform config. So we've taken care of that from that aspect. We're also bringing our own sort of OpenVPN software. So we'll ensure in Terraform that the networks and everything are completely private. And we'll ask the cloud provider to give us a public IP so that we can assign it to our OpenVPN box. But we use OpenVPN as a way to ensure that only appropriate people can log in. From the user access control side, if people need to SSH onto the box, we only allow them to do that with keys, no username and password. And if we have to manage user accounts, that sort of free IPA software that I talked to you about does identity management as well. And we are actually doubling up and using that to do our user management in the environment as well. But the area which cuts across all aspects is how do you manage your secrets? So this crops up everywhere, whether you're trying to do your infrastructure provisioning, what are the credentials that I need to connect to the cloud provider with? Once I've done that, now I need to install stuff on the box. I need to get what are the credentials to get to Git. If I've got database passwords, what are the database passwords? There's all of these secrets that somehow need to be managed. And we've got a few tools in our little toolbox here. So how do we cohesively try and manage all of this? So the lesson here is that security is quite hard. And there are probably some of you that are really good at this, and that's great. You're probably excluded from this. But for mere muggles out there, if you can leverage tools that you already trust, people have done this before, and the advice is really don't try and roll your own. So the final sort of big tool we're going to look at is Vault. Again, HashiCorp tool. Very, very, very new. We are just trialing it out at present. But it is actually being used in production by some big companies. Its sole goal is really to sort of securely expose and provide access to secrets through a tightly controlled API. So this API can be exposed either via HTTPS or a command line tool that they provide. It does more than just act as a sort of secure database storage mechanism, though. It provides, well, a pluggable backend. So if you want to store your data on file, you can do that. But if you rather want to plug a database in and have it stored that way, you can do that. You can define policies. So you can say who's allowed to access what secrets in the sort of service and who's not. It can also help you to sort of react to breaches and compromises, because you can audit exactly who's kind of accessed what and when they accessed it. So in our setup, we run a sort of centralized Vault service, and we configure all of our tools to be able to talk to it. Now, each tool generally has its own way of doing this. For example, in the sort of config management space, in Puppet, you have encrypted Hera. Chef, you have encrypted databags. But if you were to use that, you'd have to be duplicating your secrets in a lot of different places. And it's harder to change in the event of a compromise. And this very much helped us when we had to swap from Ansible to Puppet. So if we'd stored all of our secrets in the Ansible vault, when we moved to Puppet, we would have unencrypt all of that stuff, then go and put it in Puppet's mechanism for handling that and kind of move the stuff around. But because it's stored in a central secrets management database, we just need an API to be able to get it and integrate with the tool. So the integration efforts vary. Puppet already has a plugin, a Ruby gem, that you can use. Ironically, Terraform, which is a HashiCorp product, does not have native integration with Vault, which is very disappointing to me. And it is apparently coming, but it's not actually there yet. But it's very, very new, and we've had to write some wrappers around this stuff ourselves. But again, because of our principle of we want all our tools to have an API, it means that people are easily able to write plugins to integrate with this, and we can also write stuff around it in order for us to integrate with it. So how does this stuff work? So there's a sort of one-off process where Vault needs to be initialized and unsealed so that the rest of the environments can start using it. And the way I tend to describe this is it's a little bit like the movies when you see one of these missile launches, and you said there's 3 generals, and they're all in a room, and it says 2 of you have to put your key in at the same time and turn the key in order for the missiles to launch. And Vault's initialization and unsealing process works in the same way. Technically, it's an algorithm called Sharma's secret sharing, and in the event of a disaster, you can sort of seal the whole vault and close it down as well. So here's an example of the turning of the first key, so to speak. So when Vault is initialized, we've said, these are 3 possible keys that you can unlock me with. So in this case, we've got somebody who's used the first key, and they've essentially unsealed the vault, and you can see it's kind of noted, you 1 down, 1 to go. So at least one of those other 2 keys need to be used in order to unseal the rest of the vault. And then somebody can put that key in, and it will say, all right, Vault is now completely unsealed, 2 down, 0 to go. It's now available for the environments to be able to use and get their secrets out of. So now that we've got it unsealed, we need the particular environments to have the information that they need in order to do what they need to do. So in our case, they do need to go and populate the data in Vault itself. So if they have specific database passwords or whatever that are required, they need to put that in there, and if it's going to change, they also need to keep that up to date. So here is an example of the command line interface of what this looks like. So at the top, we are creating a new mount dedicated to Team 1. You can list them, and it will kind of show you the default sort of mount areas as well as the special one that you've created. And here we have an example of writing a particular secret, the cloud provider password for Team 1 into their area, and also reading that secret out. So it's unsealed. We've got the data in there. Now we've got to give it somehow to the tools in order to be able to use this information as part of its process. So the way this is done is that we get a policy, or we define a policy, which says only Team 1 can get hold of this part of Vault, and we get a token for that, and that's the token that's used and given to the bootstrapping mechanism. So here we have an example of what a bootstrap policy looks like. It will tell you that, in this case, I'm allowing a read of everything under the sort of Team 1 structure, but write is denied by default. And sort of using the command line interface, we can verify this and see, okay, if I create a token and I say this is the policy, this bootstrap policy, and it will give me back a token, I can then authenticate with that token, and all the sort of actions I perform after that will have the policy applied to it. So here we're able to read the provider's password under Team 1 because that was allowed. But as soon as we try to write something, it says, no, I'm sorry, you can't do that. So the sort of security summary here is that we've really scraped the surface. This is really only focusing on secrets management. But we have, again, stuck to our ASAP principles. It's automatable, separated our configuration or secrets data from the actual tools that we've used. That's made us easier for us to move stuff around. It's API-driven. Other people have written tools. We've written tools to be able to integrate with it. It makes it a lot easier. And it's open source, which is great as well. Centralized secrets management is very handy. It makes it easier to change because there's only one place generally that your passwords are stored, and easier to handle in a sort of compromise. And it did make moving from Ansible to Puppet sort of easier for us. And the mantra, don't try and roll your own. Somebody's already done a lot of the hard work. You can just kind of hook into it. So very quickly, we've got this stuff. It's in a particular cloud. It's all secure. It's all created. How do we move it? So the lesson here is baby steps. So the initial approach that we've focused on is more of a disaster recovery type scenario where you recreate the whole environment in a different cloud provider. So what we're not doing is we're not trying to actively migrate your data across cloud providers in real time. We have eaten our own dog food in this. So for our own sort of tooling environment, we were running in a cloud provider and we had massive disk failures, completely scuppered us, and we couldn't actually work. So we decided, right, going to go into a different cloud provider, pointed it there, spun it up, and it was 40 minutes at that stage. It's a bit lower now. We had our complete tooling environment recreated, including our restoring from backups. So the approach with this particular case is that once the sort of environment's been recreated, we did ensure that we had backups stored outside. And then after the recreation of the environment, we then used the backups to restore our state to the point that we needed it. So the conclusion here is that you need to understand that this is at least limited to a recreating scenario, not real-time migrations. And it's still work in progress in terms of the stuff that we're doing. So the final sort of conclusion for this talk is we've managed to kind of bring together a whole variety of different tools. We've got Terraform, which has done our infrastructure provisioning. We've got Packer, which has created some consistent OS sort of images for us, make sure that we've got a consistent starting point. We've got cloud-init and Puppet, which installs stuff on all the boxes and ensures that it stays that way. And we have Vault as our mechanism for storing all of our secrets and ensuring that all of the tools can hook into that. We have managed to create a secure recreatable environment in different cloud providers. And hopefully we will have happy devs because the process is not too long. There's no bureaucracy kind of involved. And management are also happy because they can see exactly what's happened. Everything is automated. They can check the firewall rules. They can check the security groups. They can be very confident that it adheres to whatever security principles are out there. So, in summary, be true to your principles, but be flexible in your tools and potentially even your approach that you take. And this will allow you to essentially evolve as your approach evolves. And cloud is constantly changing. And I think if you want to take advantage of some of the kind of newer stuff that's out there, you need to try and make sure that your tools can adapt and change as well. So experiment with baby steps, really, because if you do too much at once, it can be quite sort of overwhelming. And we are by no means done and dusted. This is an ongoing project, and there's a lot of sort of research and stuff involved in it as well. But we wanted to give insight into where we are thus far and what we've managed to achieve. So thank you very much. I think I am probably overrun, so I don't know if there's any questions. But I don't think the next speaker's here yet, so I can take some questions if there are any. Okay.
Put Apache on and PHP.
Mm-hmm.
I wanted my own index.php, and then I just wanted to start up and serve that.
Mm-hmm.
Which tool is going to do those three things?
So there are actually different approaches to this, and it depends on a few things. So some people go down the approach of installing lots of software using Packer. So instead of just having a base operating system, they almost want an immutable kind of image, which may include the software. In our case, we're not doing that. We're just having the base image, and we make use of Puppet. We would make use of Puppet to install the sort of basic Apache service, and then there would be there would probably be, as part of the Puppet configuration, there would be the setting of your files and stuff. It can sometimes be done as a post-process for the actual release cycle of the developers, though. Some people as well, so the example that I've done here is kind of using Puppet to install native software on the box, but what a lot of people are looking to do is just to install something like Docker, and then you can actually have a separate process which gives more control back to the developers, which says if you want to install whatever your PHP stack is, you just create a Docker image, and you just got to plop that into Docker, and all is well. So people are moving towards that model more than trying to create the actual software on boxes.
The only problem I see with Terraform and the cloud-init, we have some lab locally with real hardware.
Mm-hmm.
We can't work with Terraform in this case. So what do you do in this case? What do you suggest?
So we kind of ran into a similar problem. So there are not providers for all of the infrastructure out there, but there are a lot more kind of coming on all the time. And one of the clouds that we kind of wanted to talk to was a VMware-based cloud, which it's proprietary and whatever, but there are a lot of VMware clouds out there, and people kind of want to do it. So we've actually landed up writing a VMware VCD provider, and will be in the process of being open sourced soon. So in that case, for the case where we didn't actually have a root, we actually literally wrote a provider for the actual hardware in that case. If it doesn't exist, then you can't use that from that perspective. So in terms of who we're integrating with, it does cover our use cases. Cool.
So pretty interesting talk. Thanks. A question for you was around your use of vaults.
Mm-hmm.
When you are bootstrapping it initially and you go to unseal the vault,
Mm-hmm.
how are you managing that master key? What kind of controls are you putting around that key? Where are you storing it?
So maybe I didn't make it clear. We're not actually bootstrapping Vault itself. Vault is a separate external service which is managed in a completely separate kind of manner. So the bootstrapping of, we don't bootstrap Vault as a service per se. We just get the token and we give that into the environment, and then stuff happens from there. So at the moment it's manual, basically. So you will initialize and unseal the vault.
Can you give us your advice on service discovery?
Service discovery. That's another whole area. So there are a few ways on doing kind of service discovery. Are you talking about machines or for machines? So this project is evolving, and one of the things that we are going to be looking at doing is needing to kind of monitor which machines are in which environments and all this kind of stuff. And to be honest, we'll probably be looking at console as a product to do that. So I think I'm being kicked out. All right? Thank you very much.